Okay, thank you. So today I want to sort of generalize some of the ideas that we've been discussing just a little bit and tell you some more recent work connected to this formulation of supersymmetric lattice theories. So up to this point in time, we've discussed these formulations arising from discretization of continuum twisted theories, and the focus last time was mostly on n equals 4. But in all the cases we've discussed, we've really had fermions in the adjoint representation only, and we've been thinking about fixed regular lattices. So today I'd like to generalize that a little bit and tell you how you can build theories where the fermions live in different representations in the adjoint, specifically the fundamental. So we'll talk about some toy models for super QCD. And in fact, in those models, we can even engineer things like spontaneous supersymmetry breaking in a way I'll show you. So that can be quite interesting too. I'll also go through some ideas about how you might take some of these Q-exact theories and write them down on random triangulations or arbitrary triangulations. So I'll spend a bit of time on that. And then we've been talking a lot about holography in this meeting, and I'll sketch some of the difficulties that arise when you try to use these lattice supersymmetric theories to discuss issues in holography, particularly the divergence, the thermal divergence of the partition function. So I'll go through that. All right, so let me first of all talk about these generalizations to quiver gauge theories, and specifically in the end to super QCD. So I'm going to talk about a specific model. So this is a model which starts off in 3 dimensions. So I'm going to go to the 8 supercharge model in 3D that I wrote down many slides ago, or at least I mentioned it many slides ago. So you'll see that its action resembles the kinds of actions we've been discussing so far. So there is a natural Q-exact term, which looks very familiar, I hope, to you now. It has a coupling of this twisted fermion chi to this complex field strength. It has a coupling of the scalar fermion, the one associated with the scalar supersymmetry, the nilpotent supersymmetry, to a derivative on the complex bosons, and then there's a coupling of eta to an auxiliary field. So that structure is essentially exactly the same as the n equals 2 theory you looked at in the very first lecture. If you remember when we were discussing n equals 4 and how we obtain n equals 4 by a process of dimensional reduction, we actually considered a theory in 5 dimensions. In that 5-dimensional theory, there was another Q-closed term you could write down too, which was and the same is true in 3 dimensions. So this particular theory, there's a unique new term, which is supersymmetric by virtue of the Bianchi identity again, which you need in order to get back to the original supersymmetric theory. So in principle, you need this term in order to untwist the theory and get back to the original theory written in terms of spinors. So this is because we're in 3 dimensions, I expect to have a 3-form arising, and that's this theta ABC. So I can always write that as epsilon ABC times a single theta, if you want like a pseudo-scalar field there. Right, so you can see that this action is supersymmetric because when I vary the theta, I get 0. That's the new piece I have to add to my supersymmetry transformations. So theta is a singlet under Q. All the other transformations look like we had in 2 dimensions or in 4 dimensions yesterday. So this is the one new piece. So when I vary this guy, I just get a d bar on chi. Remember, a bar is also a singlet, so there's no variation from the covariant derivative itself. So the only variation comes from chi. Chi goes into f bar, and again, by the Bianchi identity, that's supersymmetric. So it's a topological-like term, which is supersymmetric. Sorry? Theta, yes, it's just another Grassmann. Right. So this is a very natural, twisted lattice action that you can write down with corresponding to a theory with 8 supercharges in the continuum. You can see the transformations you need, the way the fields transform into Q are essentially a trivial generalization of what we've talked about so far. Again, these fields will in general live on links in the lattice, so there'll be face links and a body diagonal involved. So theta will be associated with a body diagonal, since it's a 3-form. But other than that, the structure of the theory is very similar to what we've been talking about. So this is the starting point for this construction of super QCD in 2 dimensions. So I have to start in 3 dimensions to construct this theory. as you'll see in a moment. But this is a starting point, and it should look reasonably familiar by this point to you, since the structure is essentially the same as the things we've been discussing so far. Okay, so how do we start making this transition to a theory with fermions in the fundamental? So this construction, by the way, was arrived at both by Sugino effectively and also Matsuura sort of independently using Oberfold methods. But I'll talk about it in the language of twisting and show how you get there from our twisted constructions. So how do I do this? Start from this three-dimensional theory, the one I just wrote down. The first thing I do is I take a lattice with just 2 time slices in the z direction. And I'll use free boundary conditions, not periodic boundary conditions, in that direction. So the game is the following. What I want to try to do to construct a quiver gauge theory is to introduce 2 independent gauge groups, and I'm going to associate them with the 2 different time slices in the lattice. So I'm going to use a gauge group UNC on one of the slices and UNF on the other. All right? So that's fine. Any field living in those time slices, I can take the kinds of lattice terms that arise in my action, and they'll automatically be invariant under UNC and UNF on those slices. But clearly any links that lead between the 2 slices have to transform as bifundamental fields, in this case, under this product gauge group. Right? So it's possible to think about taking that 3-dimensional theory and trying to force the different time slices to have different gauge groups. That's fine, but any link between those 2 slices will therefore have to carry fields in a bifundamental representation. Right? So it's convenient to just introduce a slight change in notation, just so it's easier to see what's going on. So I'll call the fields on the NC lattice, right, the one corresponding to gauge group UNC, I'll call those, I'll use the same language I used for that before when we discussed the 2-dimensional force supercharge theory. So I'll have a U, an eta, a psi, and a chi. All right, so these are sort of using 2-dimensional language to label those fields. Similarly, on the NF lattice, the one corresponding to gauge group UNF, I'll use hatted versions of those fields. And then the bifundamental fields, which go from an x-like coordinate, the NC lattice, to an x-bar coordinate, the NF lattice, will therefore transform as bifundamentals. They'll go from x to x-bar or x-bar to x. And I'm going to call, in the end, U3, the corresponding link in that direction, phi. It'll become a scalar. This is essentially a form of dimensional reduction. Psi 3 will become effectively a scalar, a bifundamental scalar. Chi 3 mu, right, the other extra fields in my 3-dimensional theory will look like I'll just call it lambda mu. So again, I'll use 2-dimensional language to label these bifundamental fields that connect the 2 time slices. All right? But they're just inherited directly from the 3-dimensional theory. I'm breaking those fields down into subsets according to how they transform under the product gauge group. Okay? So that's just a relabeling at the moment. So here's a picture which illustrates it better. I have my UNC lattice and my UNF lattice. All right? And then these links that go between them will carry the bifundamental fields. Everything now labeled in this sort of 2-dimensional twisted language. All right? So just to make it clear, I'm going to assume that this field phi, which corresponded to U3, has to now transform with under a gauge transformation G phi H dagger, where G lives in UNC and H lives in UNF. Right? And similarly for the other fields that bridge between the 2 time slices. Right? So I'm trying to force this theory to have different gauge groups on different time slices, basically. And I can do that if I make sure the fields that link between those 2 lattices transform in the bifundamental fields. Okay? So at the moment, there are 2 independent gauge symmetries in the theory. All right? So it turns out this procedure of working down from the 3-dimensional system onto picking 2 time slices and forcing, in this case, these bifundamentals into the system retains both gauge invariance and Q symmetry. It clearly retains Q symmetry because I'm not doing anything to the structure of the supersymmetry transformations or indeed the structure of what terms I appear in the action, so it clearly doesn't violate Q. It's a bit less obvious that you can do it in a way which is consistent with gauge invariance. So let me say a bit more about that. Right? But it turns out to be the case. So let me give you an example. So I start off with a term from my 3-dimensional twisted lattice action. So chi AB, dA, psi B. So A and B running from 1 to 3. So that's one of my fermion terms. So that's the 3-dimensional thing. Let me pick up the index B, set the index B equal to 3. So now I'm talking about one of these bifundamental terms. Then using my prescription I said before, so this is the derivative that we started with. when I make this particular prescription, that forces the structure to become lambda mu, u mu lambda, x plus mu minus lambda u hat. So this original term collapses to this term. But if you follow it around, you'll see that each term in these products is actually a closed loop, and it's perfectly consistent under the two independent gauge transformations. All right? In the same way, there'll be a term when I set A equal to 3 arising from this term, which will give you a slightly different term. This will now involve U3, which becomes phi. And this should be phi hat, I think. So there's a typo here. But anyway, phi hat at x plus mu. All right. So all the terms you had in your original action sort of have a natural correspondence in this new theory where I'm taking the fields which have a component in the, if we want, in the z direction, to transform as bifundamentals. And what you see is you get something here which looks like a kinetic operator for this field lambda. This looks more like a Yukawa interaction. Right? And we'll see that in a second. All right, so everything, the prescription for derivatives actually admits this generalization quite naturally. Just because everything is a closed loop, you have a link in the top lattice, a link in the bottom, and then something which bridges between them in such a way that you can perform these two independent gauge transformations and retain in the theory, the action is invariant. All right, so to get down to super, so the moment this is not super QCD, I have these fields, these hatted fields living on the NF time slice, which in principle mean that this is what's called a quiver gauge theory. So I have two independent gauge symmetries in the game. But I can get to super QCD just by setting the fermions on, say, the NF time slice equal to 0, and take the gauge matrix, the U hat, to be equal to the unit matrix. This is basically equivalent to just sending the gauge coupling on the NF lattice to 0. That will naturally drive U to the unit matrix up to gauge transformations. And then if you look at the transformation, the Q transformations, you'll find that it's consistent to set all the fermions to 0. All right, so those previous expressions that I gave you before, here, I'm going to set this to the unit matrix, for example, and the hatted fermions are going to go away. So those previous expressions become things like this. So now I just have a trace of this bifundamental field, this lambda mu field, times a forward difference operator on lambda with U providing the parallel transport operation. The other term indeed collapses just to a Yukawa interaction between these lambda fields, the original psi fields, which are in the adjoint representation, and then the phi. Do I have, sorry? Actually, the flat directions are mostly removed by this procedure.
In the U hat?
There are flat directions associated with the two-dimensional slices, but only the flat directions associated with the bifundamental field, with the fields which bridge between the time slices are removed. So there are some residual flat directions in the I think in the two-dimensional slice, yeah.
Taking G and F to 0, does it not leave the possibility that the U's are constant and commuting?
The U's are?
Constant and commuting, as before, I mean. This,
yeah, so I think in some, perhaps you're right that this limit, it's not just a question of taking G to 0.
That's
you
right.
really just want to impose that condition. That's a better way of saying it.
That's what I was saying, yeah.
Okay.
Okay, fine.
That's right. So the original three-dimensional action is boiling down to an action on the original two-dimensional time slice involving the UNC gauge symmetry. It collapses essentially 0 on the other time slice, and these bifundamental fields, what one gets are kinetic terms for these bifundamental fields, which now just become fundamental fields in the UNC gauge group, carrying a global flavor index, and then Yukawa interactions between those fields, the scalars corresponding to the z direction, and these lambda mu fields. So all we're doing basically is forcing in two different gauge groups on two different slices that corresponds to inserting bifundamental fields, and then taking a particular limit in which the fields on the NF slice are just set to 0, and the gauge fields on that slice are set to 1. Then what one obtains, actually, is a version of super QCD. So these fields lambda mu, which carried two indices under UNC and UNF, now are only gauged under the UNC, but carry just a global flavor index corresponding to the NF gauge group. All right, so one ends up with NF fundamental fermions coupled to the gauge symmetry. And I've not violated the Q symmetry in this at all. So this is perfectly Q symmetric and perfectly gauge invariant. So what I've obtained from my three-dimensional prescription is two-dimensional super QCD with an NC gauge group and a global NF flavor symmetry. So this is a prescription in general for moving away from theories which just describe fermions in the adjoint to theories which describe fermions both in the adjoint and in the fundamental representation, basically generalizations of super QCD, typically in lower dimensions. Since you have to start from one higher dimension, you need a good lattice prescription for that higher dimensional theory. So this unfortunately cannot be used to construct four-dimensional super QCD because I would have to start from a five-dimensional theory, lattice theory, with the right fermion content, and that doesn't exist. So unfortunately, this won't give you four-dimensional super QCD.
Yeah. So this theory will still have 8 supercharges in the continuum?
No, it actually now only has 4 supercharges.
It's a 4 supercharge.
You end up with a 4 supercharged theory in 2 dimensions, having started with an 8 supercharged theory in 3.
So this is a theory with NF chiral and antichiral multiplets. Is that the way?
It's a vector-like theory still,
yeah.
Right. Right. Just as the original theory was. Right. Okay. So this is not the way the theory was first derived using Oberthal methods, but there's a very simple way to force it into this twisted prescription by simply starting from the three-dimensional theory and then making these particular choices as to how to keep which retain gauge invariance and Q symmetry. All right. Now, actually, at this point, you have some freedom to play around a little bit more. So at this point, I can add an extra Q exact term to the action, if I want to, which is a very simple term. It's just Q on basically trace of eta. Right? That's Q exact. It's allowed by all the symmetries of the theory, but it generates one of these Fayet-Illopoulous terms. Okay, so what you can do is you can add this to the action. If you then look at the equations of motions for this auxiliary D field, originally, this just said something like d bar a ua. That was the original equation of motion in the three-dimensional theory. When I use this prescription, I get a d bar u mu, where mu just varies from 1 to 2. The third component just gives rise to a phi bar term, and then this new term gives rise to a constant. So the equation of motion for the d field is changed. When I integrate the d field out, I essentially get the square of this, and so I generate automatically a scalar potential for the theory, just as in the four-dimensional continuum constructions involving this term, involving Fi terms. So I can build a theory, I can build a potential now for these scalars, which are started off as bifundamental fields bridging between the lattices. I can build a scalar now, a scalar potential for those fields, which is Q exact. All right. And if R is non-zero, as you'll see, it does allow you to play interesting games. Right, so for example, you get spontaneous breaking of Q if the VEV of this auxiliary field is not 0, right?
Question.
Yeah.
So I'm still not understanding. So you started with 8 supercharges and you lost 4 supercharges at which step?
At the point where you basically, let's see now, let's see, what's that work? Well, no, it's not a question of taking the flavor coupling. It's associated with the fact that, right. I mean, the number of scalar supercharges has not changed. It's a question of what the continuum supersymmetries are doing. Yeah, that's a good question. What stage do they disappear? Let me get back to you because I'm not sure. I'm not sure offhand. Yeah, that's a good question. All right. Okay, so spontaneous supersymmetry breaking will be indicated by the VEV of this D being non-zero. Okay, so that depends on both NC and NF. So if I sum over all the lattice sites, take the trace of D, that kills most of the terms in the equation of motion except this guy. So you can see that if this is non-zero, that implies this is non-zero. Now, whether this is non-zero or not depends on the rank of this matrix which you're building out of the phi and the phi bar. All right, so this is a standard rank argument for supersymmetry breaking in 4D. So if I have enough flavors here, if I construct this NC by NC matrix here, with enough fermion flavors, if NF is greater than or equal to NC, then I can always find a vacuum where this sets to 0. Right? So that's the supersymmetric vacuum. But if NF is less than NC, then the rank of this matrix is not big enough to zero out the piece proportional to R. So it's never possible to set this to 0. In that case, you force supersymmetry breaking into the system at the beginning. So in some sense, this Fi term allows you to engineer spontaneous supersymmetry breaking into the lattice theory. And in fact, we looked for that, and actually, there are very clear signals that's what's happened. All right, so it's a bit of a cheat. It's spontaneous supersymmetry breaking, but it's engineered in at the level of choosing the number of flavors relative to the number of colors. Okay. Right. Equivalently, you just can't minimize that potential at 0, equivalent to saying you can't set that to 0. So here's some numerical results which are consistent with that. This is a 16 by 6 lattice, so it's a small lattice. We introduce a soft SUSY breaking mask like before to control the residual flat directions and the time slices. You see that almost nothing depends on that. It's very insensitive to that, but we did it anyway. So what am I showing here? So the green dashed line here, so what we're measuring here is trace phi bar, right? So if trace phi bar can be 1, I'm going to set R to 1 in this. So if trace phi bar is 1, then I can make this equal to 0. And the VEV of D is 0. So that's equivalent to saying the VEV of D is 0. So the green lines correspond to a situation when you can set the VEV of D to 0, all right? And see, the red points here correspond to simulations where you have NF greater than NC. So indeed, the numerical results are completely consistent with the expectation that you can find a supersymmetric vacuum. The vacuum energy, if you want, is 0 along those lines. But if I take NC greater than NF, the blue points, then suddenly this moves away by 50%. It's a very clear signal of supersymmetry breaking. So this is what you would expect, the green dash curve on the basis of exact supersymmetry, of supersymmetric vacuum state, and the blue corresponds to what you actually see in the simulations. You can look at the bosonic action, which turns out to also be a good order parameter for understanding supersymmetry breaking. This is basically proportional to the vacuum energy, and so you see the same thing in a different channel. So here's what you expect. If you have 0 vacuum energy, which corresponds to the red points, NC less than F, that's the symmetric phase. If I simulate a theory with NC greater than NF, so I can't satisfy this rank condition, then I move from 1 up to 5. It's an enormous. So there's no doubt that they're able to capture the physics of what we expect associated with spontaneous supersymmetry breaking through this Fi term. So it's a spontaneous situation. It's a little engineered from the outset, but still it's sort of interesting to play this kind of experiment directly in the lattice context of a lattice simulation.
Hello. Can you get the difference between the fermion and the boson mass? Or
you could. We didn't do it. Right. I will show you evidence for the Goldstino, though. Okay. So let me go on to do that. So if the SUSY breaks spontaneously, we expect a massless fermion, the Goldstino. So we looked for that directly in what we were doing. So we can write down some interpolating operators here, O and O prime, which couple to the Goldstino. And here are some results. So if you look at this picture on the left, again, we picked some value of the gauge coupling and this parameter mu, which controls the flat directions, this mass parameter. There's a whole series of data here. All you really have to understand is there are plots which fall off slowly with time. So this is Euclidean time. This is the log of the correlation function. There are plots which are very flat, corresponding to the massless Goldstino. And if you look at those are all the red and the orange points. That corresponds to a situation where indeed NF is less than NC. Correspondingly, if I go to the situation where NF is greater than NC, you get the steep curves here. All right. So these are all different lattice sizes and whatnot, but you can sort of see the qualitative difference. The signal fault, there's a very massive state here in the situation when supersymmetry is not spontaneously broken. As soon as I dial NF, so it's less than NC, so I'm in a situation where I expect the vacuum energy to be non-zero, I find this very light state here, which is the would-be Goldstino. You might ask, why is it not exactly massless? It's not exactly massless because I use a thermal boundary condition on the system, which gives the Goldstino a mass of order 1 upon L. I can try to take those Goldstino masses and extrapolate them as a function of 1 over L and it's consistent with them running to 0 as L goes to infinity. So this all makes sense. I see a non-zero vacuum energy as non-zero VEV for the D field, and a Goldstino precisely when I expect to, which is when the number of flavors I've induced is less than the number of colors. Okay, so in this case, we were using 2 colors and 3 flavors, or 3 flavors and 2 colors for all of this work. So let's just summarize that part of the talk. So I can construct 2-dimensional super QCD with NF flavors and gauge group NUNC using just generalizations of this twisted formalism. Again, these constructions were first done using Oberfold methods, but as I've talked to you before, as I've hinted before, you can get all of those same results just directly from twisting by taking the appropriate generalizations for covariant derivatives on the lattice. One new feature is we came up with adding this Q-invariant Fi term that allows you to build non-trivial scalar potentials into the system, and those scalar potentials can be used to drive spontaneous supersymmetry breaking, in this case, in this 2-dimensional model. I point out, by the way, that in these situations, phi bar is typically not 0 as well. So when I minimize the potential, I do it with a non-zero phi bar. So these are quite rich lattice theories. These automatically also have Higgsing of the gauge symmetries, right? So there's a variable out of Higgsing depending on whether you're in the SUSY broken or SUSY symmetric phase, depending on when that minimize the potential. All right, so we have spontaneous supersymmetry breaking, and we have Higgsing of gauge symmetries, all built into this sort of lattice model. All right, and so you can certainly use the approach to build sort of Q-exact super QCD models in 3 dimensions, and Anosh has worked on that kind of thing too. So there are obvious generalizations of this, and this is, there's plenty of work that could be done here to flesh this out with, larger lattices and start talking about things like the spectrum directly to see if you could measure boson and fermion masses and see the splittings. So there's lots of things one could still do with this. So one thing you can't do is build a 4-dimensional super QCD theory this way, unfortunately, because you'd have to start with a theory in 5 dimensions with 32 supercharges, since you always go down by a factor of 2 when you do this construction. And since that theory doesn't exist, there's no way at this point to think about building 4-dimensional super QCD.
The sign of the Fayet-Illopoulous term? The arch sign of R?
Sign of R?
Yeah.
Of course, yes.
And you can see
then
that
you would see there was no supersymmetry breaking if I changed the sign of R. And we did that, actually. Yeah.
Okay.
Right, so there are various interesting things. And there's a lot known about 2-dimensional super QCD, actually. So there are various things out there in the literature which in principle you could go test using these kinds of ideas, right? Okay, any more questions? All right, so that was the first part of this talk. Sorry?
Another question. So here you did it with a particular superpotential. The superpotential you are fixed to this
Right.
the particular superpotential that comes from the dimensional reduction. But can you add some other superpotential to this?
The structure of this potential is determined by essentially integrating out this D field. This D field is quadratic, so you end up with a quadratic potential because the original action contained a sort of quadratic term for D.
So you don't have a superpotential, you're saying? Yeah, okay. This is the D term potential. I'm talking about
right.
There's no F term potential.
Right.
So can you add an F term potential by any chance? Is there a way to do it?
Not, I believe, in this lattice construction. This is actually an interesting question, because if you want to make contact with things like some of this Calabi-Yau physics in 2D, you need both the D term and the F term. And in fact, I did discuss that with David Tong in Cambridge, and we spent some time trying to figure out how to do it. And it seems like if you take this construction, you can build a D term. If you take Sugino's lattice construction, you can build the F term. But it's very hard to come up with a lattice construction which has both of them in play at the same time. And so some of that physics seems difficult to get to, at least if you want a Q symmetric or something with exact lattice supersymmetry as a starting point. So sadly, I don't know how to do that. It seems like you have to make a choice depending on the twist you've picked. Yeah, that's a good question. Okay, so let me move to the second topic I wanted to talk about, which is to see whether you can generalize these models away from this notion of living in flat space or living on a fixed regular lattice. And so a little work has been done on that by Matsuura, and I'll show you that in just a little moment, in a moment. So I'm going to again consider our favorite model, n equals 2 Yang-Mills in 2D. And the nice thing about these twisted models in the continuum, at least, is coupling them to a curved metric is very trivial, right? It's just a question of inserting root g's in the integration measure and making sure the indices pair up with the appropriate insertions of metric factors. So, for example, the model we talked about in 2 dimensions can be written in Q-exact form on a curved manifold by simply inserting a g mu nu in here and using the appropriate f here. Okay, so this is just related to the flat space f over root g, basically. Oh, it's there, in fact. There we go. All right, so this is, okay, so this is close to what we discussed before. Actually, there's a little trick here. This is not the Q-exact formulation I gave you before. It's the A-twist guy. The one I mentioned was an alternative way to discretize the theory. There was an A-twist and a B-twist, and mostly we spend our time talking about the B-twist. This is an example of how you would, if I set the metric to 1, this is essentially the A-twist. All right, so I have to use different twists of the theory, but other than that, I can easily generalize that theory to a curved manifold. In fact, when Witten originally constructed topological field theories and exposed a nilpotent supercharge, the whole rationale for the approach was he wanted to generate a supercharge which could be lifted to an arbitrary curved space, right? Which is not true in general for spinorial supercharges. So his goal and the original work on topological field theory was precisely to come up with a formulation which allowed him to produce a scalar supersymmetry which could be lifted onto an arbitrary curved manifold. So this it's very natural you can do this in the continuum, at least. All right, so notice that the transformations here are a little different from the B-twist transformations. So phi is basically a gauge parameter, so it's a singlet under Q. Phi bar goes into eta. A goes into psi still, but this is not the complex A, this is the regular A, just a pure gauge field. Psi goes into a covariant derivative of phi, and what you can show very quickly is, if you look at this, is that Q squared is now not 0, but a gauge transformation. Right? So if I, for example, let's see now. If I take Q on A here, for example, so if I operate with a Q on this again, I'll get Q squared on A is Q on psi, which is d mu phi. That says the Q squared on A is d mu phi. It's a gauge infinitesimal gauge transformation on phi. So this is not exactly the same twist we talked about before, but it's an alternative that you can certainly use, and it's been studied quite a lot numerical. So if I just set G to 1, this is the original A-twist action written in Q-exact form, right, with these particular transformations. So the question is, can you generalize this construction to the lattice in some way? And so what these guys did was precisely that. It's clear that there are naturally 0 forms, 1 forms, and 2 forms in the theory, and you should map those guys to sites, links, and faces, or plaquettes, just in the way we've been describing before. So you can introduce gauge fields which live on links, corresponding fermions on links, scalars that live on sites, and the auxiliary field B and the corresponding field chi, those were 2 forms in the continuum, so they live naturally on faces of the triangulation. In fact, this construction works on more general cellular decompositions than just triangulations. So I can actually make it work on general cellular decompositions, in fact. So I have sites, links, and faces, and I can associate those twisted fields with those subsets, right? And I can write down corresponding terms in a lattice action which look like the continuum. So if you see here, there was an eta phi bar term, basically a derivative term on phi bar coupled to psi, and this chi term. So I can generalize the structure of those terms to the lattice. So here's my eta phi bar. Here's my derivative on phi bar. All right, this is a parallel gauge transporter. And here's my, what looks like a chi coupled to B minus F term. Right? So because I write these in Q-exact form, they're clearly supersymmetric from the outset, even on the lattice. So, and again, it's natural to put the etas on the sites. The vectors are associated with links, but in fact, in this lattice construction, just like in Sugino's flat space A-twist construction, you end up putting all the fermions on sites. So the link psi is associated with a link, but it's assigned to one endpoint of the link. Similarly, chi is associated to a face in the lattice, but then you have to pick one point on the boundary of that face, and a representative site, they say, and assign the chi there. The remarkable thing is it doesn't matter which site you pick. You can show that the final theory is independent of that choice. Right? So you start by mapping them to these different geometrical objects, but in the end, you pull each fermion back to a single site to write down the lattice action. That's true in the original Sugino construction of the A-twist model too. So that's not new. That's actually already in place. Right? This function f here has to essentially be the analog of the continuum field strength, F12, but it has to be selected very carefully. Because I put all the fermions on the sites, that forces a certain structure into the lattice theory, and if you're not careful, a poor choice of the field strength will lead to a sort of a vacuum degeneracy problem. There's more than one vacuum solution in the theory. And so they give a prescription for this f, which is slightly non-trivial. All right, so here's the prescriptions. So first of all, this UF is a product of all the gauge links around the face. So again, this face doesn't have to have just 3 links around it. It could be a more general cellular decomposition. But anyway, UF is just a product of the links around the face. And then I construct the F by taking this particular combination. And what they show is that the form of F is such that there's a unique vacuum in this theory corresponding to the unit matrix. So if I set the gauge coupling to 0, then there's now a unique vacuum. It corresponds to vanishing field strength, as it should. If you're not careful about how you choose F, then you can find solutions with U equals minus I as well. And that was one of the original problems with this whole approach, which was rectified some years ago. So they're using the same ideas here. They have to construct a field strength which has a unique vacuum as I take the gauge coupling to 0. So what you can show is if I take all these, so I had some coupling constants in the game here, alpha S, alpha L, and alpha F, as well as another coupling beta F here in front of the field tensor. So you have to show, first of all, that if I take all those guys equal to 1, and I take my cellular decomposition to just be the cubic lattice, then this thing reduces to Sugino's lattice action for the A twists of n equals 2. And so that's very easy to see. So this theory, in the limit where I restrict to regular lattices, and make this choice of the alphas and this beta F, just reduces to a well-known twist of the n equals 2 theory that was written down more than a decade ago at this point and has been studied numerically quite a bit at this point. So it certainly has a well-defined limit in that way. Notice that since we're choosing the etas, the psis, and the chis, and placing them on the corresponding geometrical elements in the lattice, this fermion action is actually of the Kähler-Dirac form. So by invoking some of these theorems in homology theory, you know that this thing doesn't exhibit fermion doubling. So that's crucial. If I just take a generic latticization of the fermions on a generic random triangulation, I might worry a lot about fermion doubling. So the claim is that this fermion action does not have that property. All right? Even though the fermions are effectively always picked to live at lattice sites, because those lattice sites are associated with these geometrical objects, the claim is that this is free of fermion doubling. Nothing depends on the representative point you choose for the face F. So when I choose a face variable, I pick a site to put my fermion on. Doesn't matter which site I pick. It's gauge invariant by construction, and it's Q-symmetric construction for any random lattice. So I can pick any cellular decomposition, and I can write down this theory on that cellular decomposition, and it satisfies these two constraints. It doesn't necessarily have a point symmetry or anything like that, so you just have to worry about the renormalization of the theory, but at least it satisfies this. So let me make a few more comments about it. It's easy to show the classical continuum limit recovers the continuum theory we started with. So if I take this theory, and I choose these alphas with some very simple prescription, they're just related to the areas of the dual polygons that surround these objects, then I can show that this action reduces to my original action, the one I was targeting in the continuum, with the appropriate root g's. Right? So there's a clear classical prescription for choosing the alphas where this lattice action converges, classically at least, to the correct continuum theory, that is this Q-twisted theory lifted onto an arbitrary two-dimensional manifold. The radiative corrections can be handled by a mild tuning, at least that's what's claimed. Is that really true? I was talking to Rich about this morning. So I'm not sure this is a true statement, but the claim is that by tuning these couplings, you can make this true for an arbitrary manifold. Classically, it's no problem. Quantum mechanically, not so clear. But anyway, it's still interesting. So all right, so.
An advertisement. If you're awake on Saturday morning, I can explain what kinds of troubles you can get into.
All right, so Rich is offering to explain all of that on Saturday morning.
Explain it. I'm just trying to, just a warning.
All right. So in the continuum, topological observables are independent of the metric. Right? That was Witten's motivation in constructing these theories in the beginning, was to show that there were certain non-trivial Q-invariant observables which were metric, whose VEVs were metric independent. That was the basis of these construction of these co-homological topological field theories. So you expect this lattice theory has sort of similar properties. So it's an example of a non-trivial topological lattice field theory. If I restrict myself to operators which are invariant under Q, I should be able to show they don't depend on choice of the lattice. Right. Actually, it's not done in the paper, so I think that's an open project to show. But you might hope that something like this is true. Now, if I go away from the topological sector, that's certainly not true. All right, so if I just look at the general VEVs of observables, they will definitely depend on the metric. It's sort of cute. You can imagine if I wanted a sum of lattices. So in the spirit of the old dynamical triangulation models in 2D, which are discrete models of quantum gravity in 2D, I can imagine now summing this system over a fluctuating two-dimensional lattice, a fluctuating two-dimensional triangulation. All right? So in that way, I'm incorporating two-dimensional metric fluctuations directly into the system. The theory has this global rigid supersymmetry. So this is a very interesting system to think about, right? This is the first model I know of where you've been able to build a discrete sort of dynamical triangulation model which incorporates an exact supersymmetry. So the spectrum of the theory, bosons and fermions, is paired. You might think this is some sort of toy model for a twisted supergravity. It's not really supergravity because the Q is not local, but the metric fluctuations are local. So it's certainly an interesting thing to think about as to what actually this model looks like if I start summing over lattices or integrating over two-dimensional metrics. Another question I think which is interesting is whether this whole construction can be generalized to greater than 2 dimensions. I have some reservations about whether that's possible, but it would be interesting to know. And certainly I think you could construct theories with more than 4 supercharges this way. All right, so I think there's lots of open questions, and this paper was written a couple of years ago. There's lots for people to do, I think. Right, I think probably you would agree. Yeah. So I think it's really cute, and it's worthwhile thinking about more. All right, so the third thing I wanted to talk about today was to make some comments about the use of these supersymmetric lattice theories to study holographic dualities, connections between gravity and super Yang-Mills theories. So according to Maldacena, this maximally supersymmetric SUN Yang-Mills theory, the n equals 4 theory we talked about, in 1 plus p dimensions describes n dp branes in what's called the decoupling limit. So I'll tell you what that is in a moment. So in more detail, what it means is that if I can define a dimensional, I'm thinking of these things at finite temperature, that's where all the numerical work has been done. So I can define a dimensionless temperature by taking the physical temperature and dividing by the appropriate power of the 't Hooft coupling, depending on P. And then I can take the large n limit. These correspondences all hold only at large n, as you heard from Masanori. All right. Then in some particular regime, that is when this dimensionless temperature is small, so I'm at low temperatures, but not too small. It has to be bigger than this particular power of n, or I move to a different regime. In this particular regime, then you expect that the super Yang-Mills theory describes supergravity, right? So supergravity then gives you a prediction, for example, the dimensionless energy density. As it obviously goes like n squared, but then it has a dependence on T, the dimensionless temperature, and lambda. All right, actually, this is not dimensionless. Okay, so there's a very specific prediction coming from the leading order term in supergravity for how the Yang-Mills sort of energy density should scale with temperature. So when Masanori and other, I think there'll be other talks at this meeting, attempt to probe holography, what they're really doing is measuring this the Yang-Mills energy density, or something like the Yang-Mills energy density as a function of dimensionless temperature, and see if it matches to this particular prediction from supergravity. right? There are also predictions for things like the square of the scalar widths in the theory too. So it's not just the energy density. People have also looked at things like phi squared too. There are specific predictions in supergravity for these guys, and it depends on the p you pick. So most work has been done at p equals 0, but there has been some work at p equals 1. That is two-dimensional supersymmetric Yang-Mills. There'll be some talks about that, I think, later. And people have been trying initially to sort of see where they can match the thermodynamics between the supergravity theory and the Yang-Mills theory. If they can match the thermodynamics, it's a rather non-trivial test of the holographic conjecture in this particular context. One thing you face right away when you start doing these simulations, though, is that something that's come up in the discussions already is that all of these theories, for p less than 3 at least, suffer from instabilities at small temperatures. So precisely where you want to check the correspondence, strong coupling or equivalently low temperature, is precisely where the theories exhibit a thermal divergence. Right? So what you notice just empirically when you run code is things like the scalar eigenvalues and these Polyakov or Wilson lines start to diverge if you go to low temperature or strong enough coupling. That means that in practice you may just see your simulation algorithm just fail, just crashes, right? No longer evolves the configurations at some point. You also see strong metastability. Sometimes you can run and everything looks absolutely kosher for 10,000 trajectories, and then suddenly you see the phi square just blow up. All right. So you see lots of signs of metastability. That's when it's blowing up when this divergence is finally, the Monte Carlo has finally found the divergence that was in there to start with. Right? So there's this problem of actually making contact with the supergravity limit, because that's precisely a limit where the Yang-Mills theory is unstable. All right? And of course, there's a reason for that. The original supergravity theory it had an instability itself related to the radiation of D0 branes. And this is something that I think Masanori covered several times during this talk. So there's a physical reason for the instability, but still you have to understand how to control that instability and how to get the physics underneath the theory, the physics of the black hole, having separated out the would-be radiated D0 branes. So these are issues you have to tackle up front. All right. And that's one of the reasons these simulations are harder than you might have expected. You might have thought that in low dimensions, this should be quite an easy prospect. And it turns out not to be, partly because you have to go to large n to make the correspondence, but also because of these regulating these instabilities is crucial to extracting any kind of useful physics from it. So let me just show you where that divergence lies. You can do this in the continuum, so you don't even have to be on the lattice. And you can expose exactly where that thermal divergence is coming from. So it's associated with the flat directions. We've said that already. So the fact that there are classical flat directions is problematic for simulations if you're not careful at finite temperature, because the scalars along the flat directions can run off to infinity. So correspondingly, I can imagine expanding my fields around these diagonal constant matrices, these flat directions, plus fluctuations. And I can start writing down effective actions for the fluctuations, right? So if I do that, I'll find there's a mass-like term induced for these fluctuations just by virtue of where the scalar, where you are on the moduli space, what the value of phi mu is in the different directions. So what you see is it's a simple exercise to take the action and just expand it around these diagonal matrices to see that you have a mass-like term induced for the fluctuations of the off-diagonal matrix elements. So what I'm trying to do is integrate out the off-diagonal matrix elements to derive an effective potential for the moduli, the diagonal matrix elements. So what you see is that generically, there is a mass term induced when I have non-zero phi mu's. All right? In fact, the crucial thing is that it's the difference in phi mu that in fact counts. All right? So delta phi mu, delta phi mu. So the separation between eigenvalues. All right? So this delta phi mu is just phi mu a minus phi mu mu. That's the notation I'm using. All right. So if the two eigenvalues get far apart, this mass term actually increases. That means I can integrate it out in a one-loop approximation. Right. So that's what you can do. So you can assume the eigenvalues are well separated, the moduli are well separated, integrate out at one loop, and find an effective action for the moduli having integrated out the phi hats, the off-diagonal matrix elements. Right? So if they're well separated, that makes sense. And you generate an effective potential for the moduli, which goes like exponential minus beta times the typical separation between the moduli. Right? And so you see the problem. if the moduli, that is, so one of your scalar eigenvalues has gone off, has departed from the rest by a long way, so that delta here is large, then the effective restraining potential is going to 0 exponentially. So as I take the eigenvalues further and further apart, the effective potential constraining them gets less and less. And so at some point, there's a divergence, right? Since I have to integrate over the moduli in the partition function, if I put them well separated, eventually the potential between them is 0, and so there's an integral, you're just integrating dx. So I get an infinity from that. So in principle, there's just the partition function is strictly divergent for any temperature and any value of p, actually. This argument is quite generic. It doesn't even depend on the number, on the magnitude of this parameter p, which is the size of the dp solution. All right, so that's the basic problem. You can see, well, let's see. So this thermally induced potential just vanishes for widely spaced moduli. So the integration over the moduli yields a thermal divergence, and this is not an artifact of the calculation, of the approximation. So we did a one-loop calculation for this. But the point is the one loop becomes exact precisely in the region where the divergence occurs. So if I take the moduli further and further apart, right, this approximation gets better and better because the mass term that you're integrating out for the fluctuations is more and more dominant. All right. So this is not, although the calculation is only a one-loop calculation, it should be exact precisely in the region where the thermal divergence comes from. Right? So there's no way you can get around this by saying that you need to do a better calculation. It's just too approximate. It is going to be exact precisely in the region where the divergence occurs. Right? It vanishes at low temperature faster. So since it's clearly, so that's obvious just from the beta dependence I just showed you, but it's also clearly a 1 over n effect. Right? It's an effect just for the moduli, the diagonal matrix elements, so it's suppressed relative to the full n squared degrees of freedom. So as n goes to infinity, there's a coefficient here which is 1 over n. So in some sense, a thermal divergence is a 1 over n effect. So if its n goes to infinity, it strictly vanishes. That's why you can talk, that's why it's possible to think about the system being actually stable in the large n limit. So at the very large n limit, this term vanishes. Right? But at finite n, it's there. All right. So in the dual picture, as I said before, the dual picture for all of this is this black p-brane system is just unstable to radiation of d0 branes. So one of these eigenvalues separating off to infinity, one of these moduli becoming very well separated, corresponds in the dual gravity picture to the fact that a single d0 brane can escape from the system. Right, so there's an understanding of where it's coming from. It's analogous, but not the same as Hawking radiation. So the take-home message from this is that checking holography is not easy, and people have found that over the last few years. You have to include, first of all, to control this divergence, you have to introduce some sort of regulator term, some Q-breaking regulator, which keeps you from running off to infinity. You can't really simulate a theory which is formally divergent. So you have to put a mass term in to control the moduli, a bit like the soft-breaking mass term we've discussed. And then in the end, you have to extrapolate, you have to take large n, remove the lattice spacing effects, and then send that regulator mass to 0. Right? And that's a difficult process. There's a lot of simulations needed to get a reliable result. And the removal of this regulator can be very delicate. Okay. So there'll be several talks, I guess, in this meeting which have discussed some of them, and we've already heard some from Matsuura earlier on, which talk about exactly these sort of limits and what you have to do in order to make tests of holography in the case of p is 0 and 1. And I think we'll actually hear a little bit also about p equals 2 from Raghav in his talk, I believe. So we've just started looking at the other case that could be tested here corresponding to D2 branes, so p equals 2. But they all have the same property in common, that you have to handle this thermal divergence very carefully and try to, in order to test the holographic connections. So let me sort of conclude. I'm actually ahead of time. I've got 15 minutes left, but I'm almost done. So there's been a lot of development over the last decade plus in the construction of supersymmetric lattice field theories. So I've told you the new actions exist now, possessing one or even more exact supersymmetries at non-zero lattice spacing. We primarily focused on super Yang-Mills for most of the talks, but there are generalizations, as I indicated today, to theories like super QCD or even general quiver gauge theories. There's been some work done to generalize the models from fixed regular lattices to something sort of random cellular decomposition. And this two-dimensional model is the one example of that, but I think there are other things one could do there. These lattice actions, particularly the ones coming, if you want, from orbifolding or from the ones I've talked about mostly in these lectures, are pretty exotic compared to a conventional lattice gauge theory. So the fermions live on links. You have complexified gauge fields in the game, and they also they live on links clearly, but they're also valued in the algebra, not in the group, so that's very unusual. You have to live with, in general, with UN gauge symmetry. That can cause some additional problems from the point of view of simulations, although it's harmless naively in the continuum. Perhaps the key thing to focus on is that this very interesting theory, n equals 4 super Yang-Mills, can be done using these kinds of methods, in principle anyway. We think we understand the renormalization of the lattice theory, so we think we understand, roughly speaking at least, how to take the continuum limit. And it's very different from how you would take the continuum limit in lattice QCD. In this case, we're going to hold the coupling constant and essentially send the box size to infinity. That's at least the rough way we'd take the continuum limit, as opposed to what one does in QCD, where one has to run the coupling with the box size. The sign problem is a problem. It seems numerically to be tame, at least at modest values of the 't Hooft coupling. It's clear the sign problem gets worse as one gets to stronger coupling, and so one has to probably deal with that head-on at some point in the near future. There are plenty of applications to holography. I've sketched a couple, and I've also sketched what the pitfalls are in some of those approaches. But I think at this point in time, most of the groups doing the work have a fairly good idea how to proceed. So I think that's a lot of potential gain from following on in that path. Of course, beyond holography, you'd like to understand n equals 4 as a quantum field theory. There's a lot known about n equals 4 in the planar limit, but much less known about n equals 4 away from the planar limit. And clearly, simulations in principle, working away from the planar limit is actually ideal, right? The planar limit is the hard limit for numerical work. So in principle, there are things that the lattice simulations could bring to the table here in terms of computing non-BPS type quantities like the anomalous dimension of the Konishi operator, the thing that was brought up in the discussion yesterday of the bootstrap. Those things, in principle, could be done with this technology, and so lattice field theory, lattice gauge theory, could have a direct impact on questions of, pressing importance in more broadly in string theory and theoretical physics. I mean, it would be very nice to have, simulational confirmation of S-duality. So we can compute for example, the monopole mass along the Coulomb branch of the theory and show that it was related through S-duality to the mass of the gauge bosons. So there are lots of things one would like to do with these simulations. And also, of course, one would like to make stronger contact to some of these bootstrap bounds that we heard about yesterday. So there is lots of motivation for lots of further work on lattice n equals 4. And I hope that some people in the room might take up some of that stuff. Of course, and moving away from the planar limit by looking at things like 1/n corrections would be something that the lattice could bring to the table, which was sort of unique. Right? So, can we move away from the limit, the leading supergravity limit, where we talk only about strong coupling and infinite n, to finite n and finite coupling, and talk about corresponding corrections to the supergravity theory from quantum mechanics and also from string corrections, the 1/n corrections. And then you can ask whether the lattice brings any other perspective to the theory too. I mean, is it possible to use the lattice to learn sort of experimentally something about how geometry is encoded in the Yang-Mills fields? Again, if you have a non-perturbative regulated system like a lattice system, you can ask all kinds of interesting questions. And there's some hope that you might learn more about this also in the context of that. So I have about 10 minutes to go, but I'm done. So thank you.
Thanks, Simon. Questions?
You You mentioned, let's say, monopole masses. How do you measure the monopole masses in the...
Well, the way we've been thinking about doing it is using the various twisted boundary conditions to ensure there has to be a monopole in the system. So there are certain types of twisted boundary conditions associated with the, say, an SU2 gauge theory, where you can twist with the SU2 group or the boundaries such that you can force a monopole into the system, or at least an odd number of monopoles into the system. So in principle, you can do simulations with those twisted boundary conditions to extract a monopole mass by measuring essentially a free energy. It's hard, but it can be done. And it's been done in the context of non-supersymmetric theories by people, what's the guy's name? R2. Yeah, right. So there's been lattice work done to do similar things before in a non-supersymmetric context. So we were thinking of trying to do that precisely. And, we know. So.
Hello. Okay. I have a set of questions. So in this n equal to 4 realization, can you add a theta angle?
Can I?
Add a theta angle?
No, because I'd have a sign problem in Euclidean space. I'd love to, but no, not that I know how to do it. Unless Shailesh has some ideas. No.
Yeah.
So no, unfortunately not at this point in time, unless we have a better way for handling systems with sign problems. So maybe if you use some completely different non-Monte Carlo technique, then yes.
So another thing is, for example, in this conformal bootstrap kind of predictions, in this that Madalena was talking about yesterday, this particular limit for the Konishi is obtained in the self-dual coupling, which has theta angle and so on.
Right. Yes, we would be testing S-duality just along theta equals 0 line. Right, that would be the simplest thing to do.
But does something happen? Something nice with the sign problem if can you cancel the sign problem with the theta angle against the sign problem at strong coupling? Or is that just...
Not that I'm aware of. I mean, the origin of the sign problem in the lattice simulations is, no doubt part of it is lattice artifacts. And the question is there something beyond lattice artifacts? Presumably so. But I don't see how adding a term like a theta term can possibly cancel out lattice artifacts, for example.
Okay. So another question was that, again about n equal to 4. So at large n, the integrability has these predictions at all Tooth couplings as a function of Tooth couplings. So what is the status of checking them in lattice? Is that
in principle, one would simulate the largest n's you could deal with and extrapolate an n to n equals infinity, and that would be one check on the sort of the numerical work. And so you would certainly like to do that in some regions to make sure that everything was, in control. But in the end, the physics is actually lying at finite n that you really could. That's really interesting, right? The planar limit is understood, essentially, right? But it's a good check on the simulations, and so one would certainly want to do that.
Yeah, but the planar limit is understood in the sense that the integrability, one kind of asserts the integrability, which is understood at the small lambda and large lambda, but in the intermediate lambda, it's more a very plausible statement because.
Right.
So it would be good to check that.
So it's a bit like this 3/4 problem that Masanori was talking about. You have confidence it's all fine, but it would be very nice to have a lattice calculation that did the interpolation between the two limits explicitly for you.
Yeah, but here the interpolation is done with a particular assumption that there's an integrable model which just and which matches various things. It matches the small lambda, large lambda, but it'll be good to check it.
Yeah, I agree.
The intermediate coupling.
Just to comment about the sign problem. Typically, when you see that the sign problem is mild or not important, it's useful to consider what the theory is when you do the quenching. So is the quenched theory, how different is it from the original theory? So there are clear examples where you throw away the sign problem in at least certain formulations. You can show that the sign problem is mild because of thermal effects, where you're sort of averaging over sort of high energy states. But then when you really go to the ground state is completely different actually. So if you go to small temperatures and things like that, you can actually see.
I think it's a pretty unsatisfactory problem. We don't really understand actually why it's not a major problem, because maybe it is a major problem for certain observables. It's, if you don't really understand why the result is actually not so bad, then you don't really understand much at all, because you could be missing something big. So I think, getting insight into the origin of the sign problem or why it's relatively mild is kind of crucial for really having confidence in simulations, particularly on large volumes where you can't compute it explicitly. So the current state of the art for these simulations is maybe 16 to the fourth at this point. There's no way we can explicitly check the sign problem on that size of lattice because computing the Pfaffian is just impossible on that volume. And it's not one thing we know is that it's not, the phase is not carried just by the low eigenvalues. So one can't just look at the low eigenvalues and say I'm safe. In fact, if you did, I think you'd find you were not safe because somehow the phase is spread over the whole spectrum.
Yeah, I guess my only comment is that there are very simple, trivial problems where I can show you that the sign problem is extremely mild on certain parameters and say that the two model, that the quenching is allowed.
Yeah.
But actually, I know that the physics is completely different.
Right, right. So you have to bear that in mind, I agree. One would like to understand things a lot better so that, yeah.
Sorry, just one more question. So regarding this statement about different observables, is it the statement that has it been checked in chiral observables versus non-chiral observables, and the sign problems are different, or is
well, if we measure the Pfaffian phase and it's small, it doesn't really matter what the observable we pick is. I think there are arguments based on localization that the topological observables are pretty safe from the phase fluctuations. You can imagine adding Q-exact terms to the action, which basically force you onto into a region of the configuration space where the phase is 0 or very, very small. So I think for topological observables, you can probably even get around the sign problem. But since you don't want to just concentrate on that sector, you have to be able to talk about every observable, then you're less sure. I mean, there are for example, I may have mentioned this before, but if you run with periodic boundary conditions, typically there is an observable sign problem, even at small volumes. But if I measure something like the bosonic action, which is related to a Ward identity, so it's a Q-invariant observable, if I just throw the phase away and look at its VEV, and I know what the answer is in that case, it's actually correct. So it's a mystery, right? If I just ignore the sign problem in certain sectors, say if I run with periodic boundary conditions, actually I get the right answer anyway. That is only poorly understood, I would say, at this point. Although there are arguments through localization for how that might be, I think.
Yeah. Back to this instability. Are you saying that the theory actually doesn't exist?
Yes, I'm saying Z equals infinity.
What? Sorry.
Unless you regulate it. I mean, that's why you have to regulate it, make sure you're doing something sensible.
Right, right. But then it could be that it's like putting, say, a braking field in a magnet or something. Right. It could be that there are different theories.
As you
Sorry. That they're actually, that's not one theory, that you have to get into different vacua as you take the thermodynamic, as you take the volume to infinity, and then you really haven't defined a single theory. Is that possible? I mean, after all, on the gravity side, there's all kinds of phenomena, right?
I guess.
Because what you've written down doesn't exist, right?
In the divergence in the gravity picture is just coming from this sort of irrelevant process of radiation of these de Sitter branes, and there is physics in what's left, and it's a question of factorizing that divergent piece off.
Right. I didn't say that it wasn't physical, but I mean, it means that you don't have a single theory when you write down the gauge theory. It's infinite, right?
Right, it's infinite.
And then if you put in stabilization, you might be pushing yourself.
You're pushing it towards what? Yes.
Different theories, right?
Right.
Right. Yeah.
That's right.
Which is okay, but it's true, right? Yeah.
Yeah.
More questions?